In this video, I want to have a look at calculating the volumes of solids of revolution. So before we jump into some examples, we need to come up with a method for doing this. So for example, if we had a curve that looked something like this, and we wanted to find the volume of a solid that's created when a section of this line is taken to make a region on that number plane. So we're taking this whole region here, and we want to rotate that around the x-axis. Now we need to be able to visualize the solid that's going to be made when we do that. So if we do, we need to reflect this underneath. So start up here and come and curve in and back out. And then we can draw in our circles. We can start to see what that shape would look like in 3D. All right, so we've got a solid that we can kind of start picturing now. Now the idea is that we want to find the volume of that, but because it's changing the whole way along, it's a bit trickier. Now if we sliced this, every single cross section of that solid would give us a circle. But the problem is that all the way along, that circle is changing size. So the radius of that circle is changing depending on the height of our curve. So right at this end, that big circle, that slice that we took at the end, would have quite a big radius. Whereas in this section, if we sliced it down here, the circle that was our cross section would only have a small radius. So if this is a function, f of x, then the radius of those circles is the value of that function. So let's have a look just at one slice or one disk that we've cut out of the middle here. So what we've said is that that radius there would be the value of the function at that point. We could also say that because of the value of that function, it's the y value at that point. So our radius is equal to y. Now if we take the start of that disk to just have a value of x, and we're going to take the width of that disk to be delta x. So delta x is infinitesimally small. Okay, so it's really, really close to zero. We're taking an infinitesimally thin slice out of here. So if we had this disk, theoretically, if we chucked a thick disk out of here, then the height at this end of the disk, or the radius of the circle at this end of the disk, would be different to the radius of the circle at the other end. But because we're taking a disk that's infinitesimally small, then we can say that this disk that we've cut out is actually a cylinder. So because it's a cylinder, we know how to find the volume of that disk. It would be pi times the radius, which we know is the y value, squared, times by the height of that shape, which is our delta x. So the pi times y squared is going to give us the area of that circle, and timesing by the delta x will give us that height as well. Now if this is infinitesimally small, we want the limit as delta x is approaching 0. We want those disks to be infinitesimally small, and then we actually want to sum up all of the disks all the way between A and B. Now if you remember, this is starting to sound a lot like when we were talking about areas and we were introducing integration. So what this is going to look like if we're rotating about the x-axis is this. So the volume of revolution about the x-axis. So if we've got a region between the curve, like this red one, and we want to, it's bounded, by a curve and the x-axis between x equals a and x equals b, and we're going to rotate it around the x-axis, then we can find the volume by going pi times the integral between a and b of y squared differentiated with respect to x. Now that pi could go inside the integral as well, but because it's just a constant, we've pulled it out the front. It just makes the calculations a little easier. So let's have a look at an example. So I've just left our formula up here to help us. Our first example asks us to calculate the volume of the solid generated when the region between the curve y equals x squared and the x-axis between x equals 0 and x equals 4 is rotated about the x-axis. First thing you always want to do with this is draw a diagram. So we'll draw in our axes. We've got y equals x squared, which is just a standard parabola. And we want to rotate that, the region between that and the x-axis, between x equals 0 and x equals 4. So x equals 4 is here. So we're taking this region and we're rotating it around that axis. All right, so our formula is up here. We've got volume equals pi times the integral between a and b, so that's our 0 and 4, of y squared. Now y is x squared, so we're going to have x squared squared, which would give us x to the power of 4, differentiated with respect to x. And now we can evaluate this integral. So we're going to have pi x to the power of 5 over 5 between 4 and 0, and then we can substitute in those upper and lower bounds. So we'd have 4 to the power of 5 over 5 minus 0 to the power of 5 over 5. And evaluating that, and we'll just leave our pi as is so that we have an exact answer, we get 1024 pi over 5. And that's units cubed because we're talking about volume. These problems are very similar if we're rotating about the y-axis instead of the x-axis. We just switch a few things around. So if we've got a region between a curve and the y-axis, between y equals a and y equals b, and we're rotating around the y-axis, now instead we're going to have the volume equal to pi times the integral from a to b of x squared dy. So it's really important that what you're differentiating with is the same as what we're rotating about. So it's the way to remember that you've got it, the right formula for the right thing. The next one asks us to calculate the volume of the solid generated when the region between the curve y equals x squared and the line y equals 3 is rotated about the y-axis. So we've still got that same parabola. It's our standard parabola. So that's y equals x squared. Then we've also got the line y equals 3. Whoops, wrong button. Y equals 3. And we're going to rotate this whole region in here about that y-axis. So it's going that way around. All right, so to find our volume, we're going to have pi times the integral between a and b. Now, a and b are our y values that are our bounds this time. So that's 0 and 3. Now we need x squared. Now we've already got that x squared is equal to y this time. So that's nice and easy. And that's going to be differentiated with respect to y. So now we can go through and work that out. So we'd have y squared over 2 between 3 and 0. So we'd have pi outside of 3 squared over 2 minus 0 squared over 2, which will work out to be 9 pi over 2 units cubed. Now we've got one more example, and it's a little bit different because the region that we're rotating is bound by two separate curves. So we've got the parabola y equals x squared and the line y equals 2x. Now they intersect at the point 0, 0 and 2, 4. We're asked to find the volume of the solid generated when the region between those two curves is rotated around the y-axis. So let's draw it up. So we have the parabola y equals x squared, and we've got the straight line y equals 2x. Now we know that they intersect at 2, 4 and 0, 0. And we're going to rotate this region in here about the y-axis. So this sort of method would work as the same way if we were going around the x-axis. You just have to do things sort of backwards a little bit. But we'll have a look first at going around the y-axis. So to do this, we're going to have to subtract. Now, this in this region, our parabola is further to the right. So that means that when we rotate this region, that parabola is going to form the outside of our shape, and the straight line is going to form the inside of our shape. So we could solve this as two separate equations, or two separate integrals. We could rotate this parabola around and find the volume of that solid. Then we could rotate the straight line around, find the volume of that solid, and then we could subtract them. Or we can do it all at once. So we're going to have our volume is equal to pi times the integral between a and b. Now a is our 0, and b is our y value up here, which we know is 4. Now we need this one, so our parabola. So we need our x squared, which we know is equal to y. minus, and now we need to do our straight line. So this one isn't as straightforward because we don't already have x squared on it figured out. So from here, we know that y equals 2x. If we make x the subject of that formula, we'd have x equals y over 2, which would mean that x squared would equal y squared over 4. So up here, we'll have minus y squared over 4, and that's differentiated with respect to y. So solving that now, we'd have y squared over 2 minus y cubed over 12 between 4 and 0. We can substitute in there, so we'd have 4 squared over 2 minus 4 cubed over 12, and we'd sub in 0. If we sub in 0 there, everything's just going to come out to be 0. Now if we evaluate that in our calculator, we're going to end up with 8 pi over 3 units cubed when that red region is rotated around that y-axis. If you were doing this about the x-axis instead, then our subtraction would have been the other way around because the straight line is on the top to form the outside of our shape and the parabola is on the inside to form the inside of our shape. And obviously the inside here would have been a little bit different because you would have needed y squared, not x squared. All right, so that's an introduction to finding volumes of solids of revolution.